over to you, Jabeom.
Yeah, thank you so much. So today, my name is Jabeom Koo. I'm from Cooper Union in New York, and I'd like to talk about our recent free tape-out using the open source EDA tool. So I know all the topics, most of topics from yesterday is mainly focused on the detail and system level design. So instead of going detail about the fundamental or skill of the RF circuit design, I'd rather focus on like overall design flow that we have gone through for the tape-outs. So, and then definitely I will briefly talk about each circuits, such as how we design and what's the performance. And also I'd like to share the layout and the future, for example, plan. The background is that actually we have a NY design, kind of the consortium, like they actually support both undergrad and graduate students for the free tape-out, especially any university in the New York State. And they actually link with the company called efabless, so we can actually go smooth for any tape-outs. So, but we use the Skywater PDK, which is a 130 nanometer, which is kind of old technology compared to recent RF PDK, such as 65 or 28 nanometer. But it is a really good experience to have such kind of the flow using all the open source PDK, not the licensed PDK. So, and then another thing is there's a community channel in the Slack. So any people who are interested in the analog RF design is actually help each other. So whenever we have an issue, we can just post to the Slack so we can get a feedback. So whenever we have, for example, difficulty using the open PDK or open EDA tool, is actually we share our issues so that we can get a really good feedback. So we actually use those analog open PDK or open EDA tools, such as XGIM, using for example, to create the NA schematic and then generate the netlist. And with that netlist, we use ngSpice for any simulation. Definitely, it's not a good quality of the simulation, but for the simple or fundamental simulation, such as maybe gain over the frequency, actually we can get the really reasonable simulation results. And then by using the Magic, definitely it is used for doing the layouts. And also we use for example, other layout tool. And then definitely and NetGen is for DRC or efabless check. So by using those fundamental open source tool, actually we could successfully tape out last year. And then this is kind of the snapshot of the simulation tool using also SGIM. And also, if you see the right snapshot, that is actually the layout of the fundamental, for example, passive components, such as a resistor and capacitor and any CMOS. But among the RF circuit component, actually one essential component is the inductor, right? But the issue we had is that Skywater PDK actually doesn't have the inductor model. Although they actually use they provide the one inductor model, but it's actually more close to just ideal inductor. And when we actually figure out a kind of hand calculating method, like maybe we can just using our calculation and then to approximately get the inductance we need. And there's also another tip on the Slack channel that because this is kind of the common issue for the RF or analog design engineer has, especially who use the Skywater PDK. And we actually followed that tips, but for the RF circuit design, actually we really need a really accurate model of the inductor. So that's why instead of just using for example, ideal inductor model provided by Skywater, actually we just give up the inductor, but using the off-chip inductor. I know it's not the ideal kind of environment and it's not desirable, but we decide that, okay, it's good to just make it implement. So later, once by the way, we plan to receive the chip on this June. So once we receive the June, then actually we will just use the off-chip inductor and then just wire bonding for the test. But we actually put more priority on the implementation first. And then maybe we will go to, for example, optimization later for the accurate modeling of the inductor if they provide. So this is kind of key feature of the Skywater PDK. Like it actually 130 nanometer, and then it actually provide most of the components, such as all the kind of the MOSFET transistors, such as nominal voltage device, 0.8 volt, up to the high voltage device for the up to 5 volts. And then actually they also provide all the passive components, such as a resistor, capacitor, diode, and even a varactor. But again, we actually need the accurate model of the inductor. That is actually kind of issue that we had. But efabless actually provides a really good, decent kind of the package of all the open source tool. So we actually go a little bit, not a little bit, but most of the process was going very smooth, except inductor. And if the time is permitted, actually, I also like to share another tape-out we are working on, which is just pure digital circuit design. And efabless actually provide really good series of the scripts, so that if a student just click one button, actually, there's a script tool, scripts that generate from RTL to all the way to the layout, and also it actually integrates to the entire chip. But there's actually a supplemental slides. Okay, this is a typical block diagram of the RF front-end circuits. So as you can see, we will receive the RF signal from the antenna, and that RF signal is actually going through typical circuits such as LNA, mixer, and filter. And then once it goes through the ADC, now the RF signal will convert to the digital circuit or digital signal. And then following the DSP or digital system will handle those signal. So instead of design up to ADC, actually we decide to focus on the primary, very front-end circuits, such as LNA, mixer, and arrow. And definitely there must be questions that why there's no PLL. So PLL is actually should be located between the mixer and arrow, which tune the frequency of the RF channel. But when we just start this project, we didn't have enough time from the design phase up to the tape-out. So then instead, we just, instead of putting the PLL, which is a really important key kind of the block in the RF front end, we primarily focus on just those three blocks, LNA, mixer, and arrow. Because again, instead of hitting the really high performance, we rather focus on just implementation using all the kind of the open source PDK. And the target application is actually a 5 gigahertz Wi-Fi. And the reason why we can go above the 5 gigahertz because Skywater is actually 130 nanometer technology. So if we want to go a higher frequency, maybe close to 10 gigahertz or beyond that, definitely we need to use recent technology such as 65 or 28 nanometer. So given the PDK, so that's why we set the target application to the 5 gigahertz Wi-Fi. And then if I go through very quickly about the fundamental of how the RF front-end circuit works is that when the RF signal is actually going to the mixer, and then when it mixes with the arrow frequency, then as you can see, the F1 and F2, which is a blue signal, represent the frequency of the RF and the arrow. And then once it goes through a mixer, then there must be an output signal, which is a green line, which is at the lowest frequency. So the difference of the two frequencies will be output of the mixer. But because of the nonlinear characteristics of the CMOS, it is inevitable that any circuit, such as a mixer, should provide or should generate all the harmonic signal, which is all the high frequency components. They are undesirable, and they should be filtered out. So the thing is, to design the really good recent, for example, circuit, actually we need to handle those harmonic signal. So the thing is, in either case, we need to, for example, receive or we need to deliver the green signal to the input of the ADC. That's actually an ideal case. But again, because of the nonlinear characteristic, actually, we will have such a really high frequency harmonic signal. So then when we design the LNA or mixer even at all, then actually we need to focus on how to minimize those harmonic signal. So, and then this is just a block diagram of one performance of the, for example, LNA, such that if we increase the input power to, for example, increase the distance of the, for example, wireline or wireless communication, we need to assume, we actually, in the ideal case, we assume that the performance of the LNA or mixer at all is actually kind of the constant. But in real case, it is not. If we push the input power, then at the certain points, the performance of the, for example, LNA will be degraded. Then the input power where the gain of the LNA degraded by 1 dB, that is actually the limit of the linearity of the LNA. So that is called the P1 dB or 1 dB compression points. So normally when we design the LNA or any RF circuit, we try to enlarge those P1 dB compression points. That actually represent the linearity. And then another thing to consider is that the Skywater PDK uses a really high VDD, which is 1.8 volts. But compared to the recent technology, which uses maybe less than 1 volt as a power supply, it doesn't make sense to hit the target or aiming the target to the low power consumption. I know the recent technology trend should be low power design, but given the technology, actually then we rather focus on maybe maximizing the linearity instead of focusing on the low power. So that's why most of the simulation results or maybe performance is actually primarily focused on how to enlarge the linearity while we sacrifice the power consumption. So that's why if you see the table, and especially when we compare the recent, for example, design, we actually give up the rest of the performance, but focus on the linearity, such as P1 dB or maybe IRP3. So as you can just see or compare those two numbers, you can see that the linearity of the LNA is actually shows a higher performance. So this is just a simple schematic of the mixer. And another issue is that, again, just inductor. So if you imagine the antenna is just a single device. But to design the, for example, common topology such as a double balance mixer, actually we need to convert the single-ended RF signal to the differential signal. For example, you can imagine that we need VRF and VRF bar signal. But again, to convert the single-ended to the differential, actually we need a transformer. Transformer is nothing but just put the two inductors together. But again, we had an issue about getting the accurate model of the inductor, so that's why we give up the transformer. But just going with the really not common but old structure, which is a single balance mixer. So that's why, although we got the reasonable performance, especially for the linearity-wise, but still kind of the fall behind for the rest of the performance. But again, we primarily focus on to implement all the RF front-end circuits. So yeah, this is a local oscillator circuit. Again, local oscillator is nothing but generating really clean clock signal to down convert our RF signal to the lower frequency. So then again, as you can see the schematic, we need an inductor. So we just hand calculating to put the parasitic resistance on the inductor. So although it's not accurate, but given the except L with the model of the C or NMOS like M1, M2, actually we got some phase noise performance, which is good enough for the Wi-Fi application targets. But after we receive the chip, and by the time we start the testing with the off-chip inductor, then actually we will get more accurate results. Yeah, I know we are running out of time. So this is just a layout. I know it's really simple, right, compared to any detailed logic or system level layout. But you can see that LNA and mixer and arrow layout, most of the area is actually occupied by capacitor and the huge size of the active device. Because again, compared to just a digital primitive logic cell, actually the RF or NO signal consume a lot of huge size of the NMOS or PMOS device. And with the help of the efabless script, actually we could actually put the wrapper of this entire layout so that we can integrate into the entire chips. And that script is actually automatically connect the any input and output of the RF front-end circuit to the pad. So we could actually go very smoothly about the integration-wise. Okay, to conclude, again, it's not the ideal environment because of the less accurate inductor model, but again, we put a high priority on the implementation. And then for some reason, although we tape out on the last June, the estimated delivery is this June. So by the time of the summer, actually, we could get the measurement results. Okay. Yeah, thanks a lot for my talk.
Nice one. Yeah, this is a really good thing to see. People starting to make analog circuits in these open source flows, because I know that we're all a bit obsessed with digital, but yes, your observation is correct that there's not a whole lot of analog happening, but it's really good to see that it's starting to. So you said it's only a 5 gig receiver, or 2.4
yes.
as well?
Actually, after we decide to use off-chip inductor, then actually we have a freedom to choose the operating frequency.
Oh yeah. Okay.
Then actually, depending on what inductor model we use as an off-chip, we can actually choose either 2.4 or 5 gigahertz.
Yeah, okay. And you said for the LO, you said you've not done a PLL, but you're just going to direct inject the frequency that you need?
Yeah.
Yeah, okay. All right. I mean, that's fine for, just to test your LNA and your mixer and stuff. Yeah, cool. Sure.
Thank you for presentation. I wonder that have you ever considered to use Skywater PDK on Cadence Virtuoso?
Yes, that's actually really good questions, because for the really accurate simulation such as a phase noise, actually the OpenEDA tool didn't give us the accurate simulation results for the phase noise. So that's why only for the phase noise simulation, yes, actually we migrate to our server, the OpenPDK, and then actually we use the licensed tool such as Virtuoso of the Cadence only for simulating the phase noise. Yeah.
Noise point was my second question, but you already answered it. Thank you.
I think Mohammed had a quick response to that.
Yeah, just a quick comment on the Cadence. So Cadence has, seen the attention to the Sky 130, the open source version of the process, and they developed their own entire Sky 130. You can download it from the Cadence website. It's not open source. The big warning that I want to give to everyone here: if you use that and you put the work out open source, it is not actually. It might be used by somebody else for commercial reasons. That's against their agreement. So just be aware. Meaning that just to try to design, make up whatever you want to do with the open source tools first.
Yes, actually we downloaded the 2 versions of Skyward. One is a commercial version, the other one is just open PDK. But as you suggested, we actually follow the open source PDK. Yes.
So it wasn't clear, and I might have missed this at the start. So what was the experience level of the designers and the layout, effectively the design and the layout engineer doing this? Was it you or was it students or?
Oh, both. Actually, I and my students actually doing the layout together. Yes.
And was that grad student or undergrad?
This project is actually done by senior students.
Okay.
The undergrad, because I normally support my graduate student for the recent technology such as 65 or 28 nanometer.
And what was the kind of experience level of that? Was that like final year capstone level with experience of analog design?
Yes, actually, my school, the Cooper Union, is actually ask all the senior students to have, for example, select the topic for and drive the entire 1 year. So that's why we could actually start the designing from the early of the senior year and then to the 1 year. Yeah.
What's the long-term goal for this design, at least in terms of your work? Is it to get like more or less functioning, like on the Skywater piece? Are you just going to kind of do this and test it and move on, or do you intend to spin again and improve? Or
Yes, definitely. This is the first step about using the Skywater and with the efabless help. And right now, the first goal is the implementation, but we will move on to, for example, optimize for the high performance RF circuit design.
yeah, because I think one amazing project would be if we had like a 2.4 or 5 gig RF front end. Yeah, because imagine if we had that piece of componentry available as an open source library for Sky 130, and then, you know, there's a bajillion 2.4 gig protocols you could then do the DSP and kind of Mac and Phi for.
Maybe that's a good discussion for tomorrow.
Sure. Anyway, Jabeom, thanks so much. This is fantastic work.
Thank you so much.
Coming along. Cheers.